Power functions. A power function is a function in the form f of x equals k times x to the n, where k and the power n are non-zero constants. So all they're saying is that the only variable in this equation is the x. Even though it looks like you have variables, they're just representing that it's going to be some number times x, and x is going to be raised to some number, okay? Which is different than an exponential function where your variable itself is in the exponent. This is called a power function. You are taking a variable to a power. That's all this means, all right? And so there's certain things that start to develop with power functions that you can kind of figure out what's going on with your function based on the power itself or the exponent that you have. And so if you look on page 25, you will see some of this information. So it says functions such as negative 3x squared or y equals 2x to the 1/3 or even y equals 1 over 5x to the 4th are power functions. These are all some variable to a power. But you'll notice it says y equals 2 to the x is not a power function. The difference between these is here, my variable is in the exponent. That's a different type of function, which we will deal with later when we do logs. This is the variable is the base. The variable is the base, all right? This is not a power function, y equals 6. That's just a horizontal line, so that's a linear function. All right, so these are power functions. While the exponent n can be any rational or irrational value, we limit our discussion in this section to integral exponents. The simplest power function y equals kx is a linear function through the origin slope of k. So we have a little bit different here. We have y equals k to the x, where k is a non-zero. All right, and in this case, my slope is not a non-zero here. So they give us a little bit of information. Y equals x squared is one that's pretty standard. This is a parabola. It's called a quadratic. You'll notice that my domain is all real numbers. This is a continuous function, all right? This is a continuous function here. Cubed, that's a continuous function, all right? There are going to be some that aren't, so obviously like this would not be continuous, but these two are. Examining end behavior. So this is actually a pattern that starts erupting with power functions. They have just x squared here and just x cubed here. But the truth is, if you have an even power or an even degree, then both sides of this are going to go the same direction. And we're going to start adding to this. But in this case, we have a positive function. Both sides are going in the same direction. And in this case, they're both going up. For this one, if you have an odd function, they're going to end up going different directions. So you'll notice for this one, on the left side of it, it goes down. And on the right side of it, it goes up. This is just another way to notate it. Okay, so you'll notice that down here, x towards negative infinity. Well, that's just this side of the graph, right? All your negative x's. And here it says x towards positive infinity. That's all your positive x's. So all you're doing is basically telling me what's happening on the left side of the graph and the right side of the graph, right? Same thing here. As x goes to the negative, I'm going down, negative infinity. As x goes towards the positive, I'm going up, positive infinity. And that's what will always happen with functions that have an even degree or functions that have an odd degree. This right here. All right. I have an odd exponent. No matter what happens in the center, the left side's going to go continuously up. The right side's going to go continuously down. We already decided it was continuous, so it doesn't matter what happens in between. I know I'm going to go continuously down on the left, that's negative infinity, and continuously up on the right, positive infinity. So then we have terms that are very, seriously, don't overthink these, right? If the function is getting larger from left to right, it is increasing. That makes sense. If it's getting smaller from left to right, it's decreasing. And if it's staying the same, it's called constant. Again, they use notation. F of x2 is bigger than f of x1. That just means it's getting bigger. F of x2 is less than f of x1. That just means it's getting smaller. All right? And then we have these terms even and odd. And you may have seen these before. A function is even when you can plug in a negative x and it equals the same thing, like this guy right here. Y equals x squared. I can plug in any negative number and it doesn't change. So if I replace my x with negative x and square it, I end up with what I started with. All right, that is an even function. But that's not the case for this guy. If I have x cubed and I plug in a negative x for that, what happens? Well, it doesn't end up being x cubed. It ends up being negative x cubed, right? Which is the negative of what I started with. That's an odd function. That's an odd function. So if you can plug in a negative x and you get the same thing you started with, that's an even. If you plug in a negative x and you get the opposite, it's called an odd function. And you can see why, because your even exponents are going to power each other out with your positives. Your odd exponents are not, right? Your odd exponents are not. So this next one says describe each function. Graph the function. And we're going to hold off a little bit on graphing just because I want to do some sketching first. Describe the domain and range. Describe the end behavior. Tell me if we have any continuous problems. Is it continuous or discontinuous? And then we're going to look at increasing, decreasing, constant, and whether it is even or odd. All right, and we're going to do just a few of these. So we're going to pull a little bit of them out. We're going to look at domain and range. All right, so we're going to look at domain and range and end behavior. And we can at this point look at continuity. All right, and then we're going to jump to, is it even, odd, or neither? Even, odd, or neither. So let's look at these. Domain. So domain is my x values. Are there any x values that would cause a problem here? 1/4 times x to the 5th. Do I have a radical that I need to worry about? A square root? No. Do I have a denominator? My denominator is actually 1/4, but do I have a variable in the denominator where if I plug something in, it causes a problem? No. So the domain here is all real numbers. My domain is all real numbers, right? So then my range, all right, if I look at this and look at range, range is my y value. And really, I'm going to think about what happens to this graph before I answer this question. I'm actually going to look at the end behavior first, okay? So remember end behavior, I'm going to look at this guy right here. It's a 5, all right? If we go back to, if I look back at this one right here, I know odd exponent means I'm going to go down on the left for now. We're going to add to it, up on the right. I don't care what happens in between. I know that's what's happening, which means my y is going to go from negative infinity to positive infinity over the whole graph. So then my range is going to be the same thing. My range, which is my y value, is going to be, again, all real numbers, because that's what my graph is going to do. It's continuous. I've already decided that. And then I know from that odd exponent that I'm continuously going down on the left and continuously going up on the right. All right? And then the last thing they want to know that we're going to look at are the last two things. We know it's continuous. So we know that it is continuous over all numbers. So we have 1, 2, and 3. And then we're going to say even, odd, or neither. If I were to plug in a negative x, what's going to happen? To the 5th power. Negative x to the 5th power. Is it going to negate this function, or is it going to keep it the same? Any negative to the 5th power. What's it going to be, positive or negative? It's going to be negative. So this guy is odd. He's odd. Now this is one they didn't talk about, but we're going to talk a little bit about it. Domain and range. All right, domain and range. The domain piece is easy. So let's look at just domain. There's not an x that causes a problem, so that's all real numbers, all right? This guy's actually going to start for y values. It's going to start at 0. There's no way my y value is ever going to be positive. Why is that? Why do I know by looking at it that my y value will never be positive? Right, they threw a negative in here. So I have negative 2 times x to the 4th. All right, x to the 4th will always be positive. Why? Why will x to the 4th goes to an even power? So if I plug in 2, I'm going to get a positive. If I plug in negative 2, I'm going to be positive, right? So the smallest number that I can get here is to plug a 0 in, right? That's the smallest I can get. And if I plug a 0 in, my y value will be 0. Everybody agree with that? So if this is always positive, multiplying it by negative 2 will make all my other y values always negative. Does that make sense? So while my x values can be anything from negative to positive, my y values really are going to start at 0. That's the lowest I can get. My y values are going to start at 0, and they're going to go to negative infinity. So my range is going to go from 0 to negative infinity. That's all that can happen here. That's all that can happen. All right? So when they're asking if it's continuous, I've kind of already answered it because I already know my domain is all real numbers. If it weren't continuous, I would have said, hey, I can use any x except for 1 or any x except for 2. And then it wouldn't be continuous because I know I have a break in the function, right? But when I've already said I can plug in any x value and they all work, then I also already know it is continuous. All right, I already know the answer to that one as well. Now here's the thing. And we'll talk about end behavior, which is why we're gonna talk a little bit about that. End behavior for this, they're gonna go the same direction. The reason I know they go the same direction is this guy's an even exponent. So on even exponents, they're going to go the same direction on both sides, no matter what happens in between, but they can go the same direction down as well. In this case, I've already said we're going to start at 0 for y, and then my y value is going to go to infinity in the negative. I've already said y can't be positive. So when you have a negative number in the very front with that even, then your end behavior looks like this. They both go down. If it had been positive 2x to the 4th, both of my ends would have gone up, right? And we're going to, in the next section, we're actually going to create a chart with what happens on end behavior so that you can see the difference. But we look at both the leading coefficient, which is the number in front, and we look at the degree to decide what happens on the ends. All right, for domain, are there any x's that cause problems for you? No, right? There's no denominator we have to worry about. There's no radical we have to worry about. From an implied standpoint, there's no issues for x's. So for my domain, I'm going to say, well, x such that x is all real numbers. You can write it that way, right? You could go negative infinity to positive infinity. They both work. All right, so for domain, no problems, which means I've already answered the next question. Is this continuous? Yeah, if I have no problems in my domain, then yes, this is continuous. Those go hand in hand, right? If my domain is any real number, then I have said I don't have a problem. Now, if it were piecewise, you could still have a jump because you could cover everything. You could just jump. But with a function like this, if there's no problem with your domain, then there's no problem. All right? What about even or odd? Again, it's right in front of you. It's odd, right? If I plug in a negative, then it's going to go back to where I started from. It's going to go to the opposite, right? If it was to the 4th power, it would go back to where I started. If I plug in a negative, it's going to actually change this one to positive, which is opposite, right? Because I have a negative times a negative. All right? So this is odd. And what about the end behavior? Does it go the same direction or different directions? If it is odd, if it is this guy right here, it's going to go different directions, right? Different directions. Or opposite directions. So we've talked about positive exponents. We can look at what happens at the end for positive exponents. Even are going to go the same direction. Odd's going to go different directions, right? We actually move towards zeros when we look at negative powers. The reason this is, remember, a negative exponent puts it in the denominator, right? So if I have x to the negative 1, I technically have this function, right? Y 1 over x. Everybody see that? So then what happens at the end is that my y actually moves toward the number 0. Why would it do that? Well, let's see what happens here. If I have from the left-hand side, so let's say I pick a negative number and plug it in here. All right? I have a negative number and I plug it in. We're just going to pull some and see what happens. So we're going to go to the left, or as x moves to towards negative infinity, okay? If I pull like negative 10 and plug it in, y equals negative 1/10, right? What if I do 100? Negative 100. Well, that's negative 1 over 100. What if I do negative 1,000? X is moving towards negative infinity. Well, that's negative 1 over 1,000. Are my overall numbers, where are they moving towards? They're moving towards 0, right? Those are getting infinitely smaller fractions moving towards 0. So what's happening to this graph is, as my x goes this direction, I'm actually doing this and moving towards 0, okay, with my y value. So as my x gets further down the number line, I'm moving towards 0. What about with the positive side? Well, with the positive side, the same thing's actually happening. As I move this direction, let's say I put positive 10. That's going to be 1/10, right? So if I'm at 10, I have like, let's say this is 1/10, all right? If I pick 100 way down the line, we're at 1/100th. We're getting smaller. If I pick a positive 1,000, I'm still moving towards 0. I'm just moving towards it this way. And so y is not going to go to infinity on one side or the other like when we had a positive exponent. When x is to the negative 1 power, on both sides of that equation, I'm actually moving towards 0 as I get further away and further down the line. I'm moving towards 0. And that's what those graphs look like. They look like kind of a strange parabola because he's actually coming from here. Kind of a sideways crooked one is when you get it that way. But they're both moving towards 0 because while my denominator gets larger, the overall number gets smaller. 1/4 is bigger than 1/8, which is bigger than 1/16, right? We're getting smaller as those denominators get bigger. So this is a special type of function. Your end behavior is going to do something different when you go to negative exponents. Types of functions that are in the format y equals kx or y equals kx to some number. And so these are types of direct variation. All right, direct variation, when you see this word, you want to think, okay, every time x varies by a constant, y is going to vary. Direct variation. The most common type of direct variation that we use is y equals mx with a zero as our y-intercept. Just y equals mx. Y equals x times some number. So if you can get to y by straight multiplication without anything else, you have direct variation, all right? That's like y equals 3x, y equals 4x, y equals 1/4 x. It doesn't matter what that k is as long as you can just multiply. So when an object is traveling at a constant speed, the distance traveled varies directly with the elapsed time. Okay, so lots of words. What does that mean? If you are driving 60 miles an hour constantly, then how far you go is directly related to how long you drive. That's all that's saying, right? So if I'm going 60 miles an hour, how far I've traveled would depend on how many hours. If I've gone 2 hours at 60 miles an hour, I've gone 120 miles, right? 60 miles an hour for 3 hours, I've gone 180 miles, right? That's all that's saying. When an object's traveling at a constant speed, the distance is directly related to the time. It varies directly. So if it took 2 hours to travel 50 miles, find the distance traveled in 7 hours, all right? So what are they saying? 50 miles is how far I traveled. They told me the distance varies directly with the time. So when you see those, they're telling you how to set it up. The distance, D, varies directly with time, T. And so we have some constant in front of time. All right. So they've told us how to set this up. And then we're going to plug in what we know. We know the distance. That's 50. We know the time. That's 2. And we're going to put the K on that side. So we know our constant is what? If I was solving for my constant would be 25. That represents how fast I'm going, right? 25 miles an hour. Easy. Find the distance traveled in 7 hours. Well, once I know how fast I'm going, I can just multiply. The distance traveled in 7 hours is going to be that K that I found, 25, times the new time they've given me, 7. And so in 7 hours, I will have gone 175 miles. That's all direct variation tells you. All right. If they say it varies directly with something, they mean set him up equals some constant times my other variable. Let's look at the next one. The volume of a sphere is directly proportional to the cube of its radius. All right. So on the left-hand side, the volume, right, is, so we're going to say equals. And then we have directly proportional. So we have some constant. And what is it proportional to? The cube of its radius. Well, I would write that R cubed. That's how I set that problem up. The volume, that's my variable, is always an equal sign, right? Directly proportional, so I know I'm going to have some constant times whatever it's about to tell me. Cube of its radius. Cube of its radius. And so I've set it up. If the sphere with a radius of 6, which variable did they just give me? V, K, or R? What did they just give me in that next sentence?
It gave you V, right? No.
The sphere of the radius. The sphere with a radius. So they gave me my R. So I'm going to plug the 6 into my R. Has a volume of 288 cubic centimeters. Now they gave me my volume. They want me to find the volume with a radius of 12. So what do I need to solve for? I need to solve for my K, right? So I'm going to say 288 pi equals K, I don't know that yet, times 6 cubed. All right, 6 cubed. So how do I solve for K? Well, I divide by 6 cubed. So I'm going to say K is going to equal 288 pi over 6 cubed. It actually reduces all the way down to 4 over 3. You can actually put the 6 times the 6 times the 6 and reduce it out. So 6 will go into it, 6 will go into it, and then you can divide by 2. So you're really just doing reducing a fraction here. But if you don't like that, you may have to divide, but you'll get a decimal. So you have to think of it this way. Right? See if 6 can go into it, which it will. And so I'm going to say 28 divided by 6. What do I get? Any takers on that? So if I reduce it, right, we can get 4, 48, 8, right? Reduce that again by 8, 8 over 6. We can now see that reduces to 4/3. So just do reducing of fractions there. All right, so this whole thing reduces to 4/3. So 4/3 pi is my K. 4/3 pi is my K. All right, once I solve for K, they want me to find the volume. Radius is 12. I'm going to go back and plug it in. So I now know my K is 4/3 pi, which hopefully you know this formula. 4/3 pi r cubed is the volume of a sphere. All right, and they want the radius of 12. So now I'm just going to plug it in. Volume equals 4/3 pi 12 cubed. And I don't expect you to do that in your head, but you can put that into a calculator. All right, 12 cubed times 4 divided by 3. 2,304 pi centimeters cubed. All right, so anytime you see the word directly proportional, what came in front is going to be set up first, then equals, then a K, then whatever they said it was directly proportional to. You can be directly varied to just X times some constant, or x squared or x cubed. You can have inverse proportions where it says inversely proportional, meaning the x is going to be on bottom. All right, so there's a lot of ways they can talk about proportion or variation, and you just have to read it from left to right and say, okay, what comes first? How does it vary? What does it vary to? All right, and so you're going to look for direct, meaning just multiply, or inverse, meaning it goes on the bottom. All right. This one. The first thing they told us is stopping distance. That's what should have stood out when you read this, because it says stopping distance of a motor vehicle is directly proportional. So this tells you why. Y is, that's equals, and then it tells you what it's directly proportional to. It's directly proportional to the square of the vehicle speed. So they just gave you your x, and they told you to square it. Square of the vehicle speed, okay? So that's where I get y, that is my stopping distance, is directly proportional to the square of the vehicle speed. So x squared is what I'm squaring, and then I have some constant in front of it. You're always going to have a k in front of it, some constant that you're looking for. The next thing they're going to do is they're going to give you one scenario with both pieces, okay? So the next statement said it takes 96 feet for the vehicle to stop. They gave me the stopping distance, 96, right? When traveling 40 miles an hour, they gave me the vehicle speed, 40. So I plugged those in. I plugged in my 96 and my 40 so that I could stall for this constant. 40 squared is 1600, divide both sides by 1600, my k is 0.06. Now that I know my k, I'm going to plug it back into my original and say, hey, this works for any stopping distance and speed, because now I figured out what that k is. And now the next statement is going to give you part of it and tell you to solve for the other. So now they're saying, I want you to give me the stopping distance for a new speed. The new speed being 60 miles an hour. Well, now I know the k, and now I know my speed. Plug it in and solve. 60 squared is 3,600 times 0.06. I'm going to get 216 feet. That's how long it takes me to stop a car going 60 miles an hour, which is, by the way, why you keep a distance between you and the car in front of you, right?